Okay, hi everyone. Welcome to Digital Futures Young Series live session. I'm Sina Mustafavi, joining from Delphi, Netherlands, moderating the session on behalf of Digital Futures. This session is joined by Digital Futures Young Committee and organizers and Neil Leach. For today's session on robotic fabrication, we have a very interesting lineup of speakers joining us from different places. Through the Robotic Fabrication Open Call, we have received a fascinating collection of projects, and this will be the first session out of the three that we will have on architectural robotics. This session will be live streamed on YouTube and Bilibili. Please feel free to leave your comments and questions, and we usually try to answer all of them during the panel discussion after seeing all the presentations. For updates, uh, you can visit our website, digitalfutures.org, where you can also find links to our archive as well as links to Digital Futures social media. We also would like to invite you to our active Discord channel with a growing community. Here we are going to share the link to the chat box of YouTube and Bilibili, and we would be more than happy if you could join and contribute to interesting daily and weekly discussions. Last but not least, in addition to Young Series presentations through the open calls, we have three other types of events, which are taught by Digital Futures instructors, keynotes, and special events. While talks, keynotes mostly focus on the themes of the open calls, such as AI, computation, and robotics. With the special events, we are trying to extend the reach of these disciplinary subjects. For instance, last month, we had a very interesting session on the future of education, and currently, to name a few, we are planning the upcoming special events sessions for other relevant and exciting subjects such as Africa, Amazon, and space architecture. So do stay tuned for the upcoming talks, keynotes, and special events. To start with today's sessions, we invite the first speaker, Ashish Mohite, to share his screen. Ashish is an architect finishing his PhD at Aalto University in Finland with the topic of digital fabrication and architecture. And he's also a co-founder of a concrete 3D printing company called Hyperion Robotics. He also holds a master's degree from SAC in Frankfurt and a bachelor from Patil College of Architecture. Ashish, you may start.
Yeah, thank you for inviting me for this talk. I'm sorry, I'm having some trouble here. You guys hear me?
Yes.
Yeah, okay. So I'll to start with my talk. This is a few years of my work from my PhD. So I'm almost finished with my PhD. I have to submit my thesis now. So the topic of my PhD is about speed of deposition, vehicle for structural and aesthetic expression of CAM. This presentation is divided into two parts. The first part is about the theoretical background, what is I'm trying to do. And the second part is actually the practical examples, the experiments which I did. So as we know that architecture is a true symbol of our time, architecture has a very close relationship with technology. But as you know that in second digital turn, Mario Carpo is arguing that architecture is always lagging behind the technology. And now when we started the first introduction of CAD and architecture, there was this disconnect between what we do, like the maker, and what the building is built, because we are designing it on a screen, and actually the building is built by the drawings. And then in the early 90s, when the experiment started in computer aided in manufacturing, there was this experimentation which was objectile, where the generic algorithm was devoid of the specificity, but it had the potential. And this is where all the thinking started, how digital fabrication can be used as a process in the design, and how it would influence the way we build. And now we are having this computational revolution where, as you know, that there's no gap between the thinking and making. So the thinker is also the maker. And then we can dive into the topic of digital craft again. Like we are now this kind of digital designers and makers. This gap is narrowing. So as you know that architecture was always we were making drawings always. We are not actually building. But now with digital fabrication, we can actually also build and create this kind of notations, which are the code. And in order to have this kind of digital craftsmanship of in architecture, what I believe that we need to have two things. One is this kind of continuity of the authorship. So the designer is also the maker, and the object itself is a process model, right? So what I believe strongly and what I like to argue is that we are no longer designing the form that will be ultimately produced, but we are designing the process. So this is what I'm interested in. I'm interested in this process of making with the digital fabrication tool, and what comes out of the process because of the material, because of the tacit knowledge. But then there is also this kind of there lies a risk of like control. There is this kind of risky craft of digital making with which Branko Koller, which also quite rightly said that this digital making, this risky craft is inseparable from the notions of glitch, errors, and unexpected results. So you have to be like very careful about what kind of control you want and what kind of lack of control you want. So this lead to this kind of surface variations, which I'm interested in, and what I call this kind of rebirth of ornament, which comes from the process and from the materiality. So all the experiments started from this one accident, which I had like back in 2014, when there was this digital model. I built this ceramic printer, and then I printed that digital model, and then the result was like completely different than what was the digital model. And I was like interested, like what actually happened? What is this unstable space in between of the making and the material, which produced this form, which actually I never designed. So this form actually came from the process. So I started experimenting. So first I started 3D printing with plastic, and the only parameter which I changed is the speed. So in this example, for all of the examples, what I'm going to show are mostly cylinders, and all what I change in the code is how the printer moves. So let's say when the printer slows down, it deposits more material. When it is moves faster, it deposits less material. And I try to observe what kind of surface artifacts are created from that. So as you can see, the surface artifacts start to create like start happening from the process of the printer moving. As you can see, like all these is not designed, it comes from the process. And then I start changing the parameters more, I changing certain rotations, I start changing the speed more and test more. So as you can see, like again, like all the original objects are just cylinders, and all what I change is the speed at which the printer moves and the amount of material it deposits at certain points. And just from the movement of the printer and the material, and in this case the plastic material, you start getting this kind of surface artifacts which are undesignable, which are coming out of the process, these textures which are coming out of the process. When I wanted to make some holes, I again started changing those parameters, and then because of stringing in plastic, I started getting this kind of holes. So again, remember that it's always about just a cylinder form, and I'm changing the speed at which the printer moves. Then I moved to another material. I wanted to see like how the material has the effect on the output. And these are the same kind of results which I get from a different material. In the first case, it was plastic, and in this case, it was ceramic. So as you can see, like ceramic, because of the viscosity of the material and ductility of the material and the effect of gravity on the material, you can start getting like different results, let's say from plastic. And I start comparing those results now. So here is like side by side, the same kind of code, which is there for plastic, and then the same kind of code, which is there in ceramic. And you can see already like what kind of different results I'm getting out of that. So then, like, what kind of architectural implications this brings was always the question in the background. So I started also experimenting now with metal welding. So this is 3D printing by metal welding by welding robot. And I did the same experiments again. And now I'm comparing like three materials, how the materiality actually affects the object. So again, like here, the process, I'm just designing the process, and I'm trying to see how the materiality and how the movement of the printer actually affects the outcome. Now, in order to check like what would be the architectural implication and the mention of ornament, which I mentioned before, to test it. So what I did is like I did series of arches, and then checked where the arch actually starts to fail. And I wanted to apply my effects of the speed of deposition to that and see what actually comes out of it. So this is a series of experiments where this is the first experiment where you can see like this is without my effects, and you can see that the arch is failing. And I did like caramba analysis of structure analysis, and then it gave me where I should add more material. That means where I should slow the printer down and where I should make the printer move faster. And this was the result. So that, as you can see, like next to each other, this is the model which is without the effect, and this is the model which is with the effect of the speed of deposition. So now in this case, it starts to emerge that this kind of speed of deposition textural effects are starting to become ornamental. So why ornamental? Because now if you remove the ornament, this is the object. That means the object is failing. So this is like starts getting this kind of notion what was there in Gothic architecture where ornament is actually structural. So without the ornament, the structure will fail. So this was another experiment where the structure is failing. The arches are like moving in one direction. And because of this kind of deposition of material, the arches are stable. Another one where I did this were like four tall columns, which were also moving in one direction because of the load. And then with the speed of deposition, they are stable. Then I wanted to scale it up and make a large scale prototype. And this was the large scale prototype where again, like as you can see on the bottom, there is more mass, there is more material, because this is where more mass is needed. And as you go on the top, as you move up and up, the speed goes faster. So that means the printer deposits less and less material, and you can print like a stable structure. So now the next question is like, how do you scale it up to architecture? And I remember once from Neil's lecture, he had this King Kong example where, like it's not that easy to scale up like small scale prototype into real architectural scale prototype. And that's when I also started this concrete 3D printing company as Hyperion Robotics. And now the idea is that once my PhD is over, I will take these experiments to the larger scale, to the scale of architecture, and try to apply what I learned from the speed of deposition in the scale of architecture and see what kind of surface texture, what kind of ornamental implication it has. This is all I have. Thank you for listening. And thank you again, Digital Future, for inviting me for the lecture.
Great. It was really interesting presentation. I'm sure there are a lot of questions and topics that we would address later on. So we move to the next presenter, Maurizio Barbero. Maurizio is an architect and researcher holding a master's degree in architecture from Polytechnic of Paris and a PhD from Roma Tre University. He's the co-founder of a new fundamental research group in Bari and also co-founder of Barberio Colella Architects. I would say when it comes to stone and digital fabrication, we see some very interesting and professional projects coming. A new fundamental research in Italy, which with its rich stone craft culture is not surprising. And here we are very excited to learn more about it. So Maurizio, you may start.
Thank you very much. Thank you, Sina and Digital Futures for inviting me. Hello, everyone. The title of my presentation is Robotic Stone, the Evolution of Stone Design and Fabrication in the Digital Age. And I'd like to start my presentation talking about the place where I come from. I was born in a region called Puglia in the south of Italy that is characterized by the millenarian use of stone for building architecture. This is what you see in the video, the Bari's Basilica, which is the best example of a Puglian Romanesque architecture from the Middle Age. So this is my cultural and architectural background. And I have started this presentation this way because I believe we should design differently depending on where the building will be located. I know it's not always possible, but I think it's important to study the characteristics and materials of local architecture prior to start designing. And this is important in order to preserve and evolve the history of local identities. And I like to start from history when I design something. This is, for example, this is particularly true for stone architecture because it has centuries of history behind us and a huge heritage that constitutes some of the best architectural example of the past in obviously where the stone is available. For example, this is a volta stella, which is a stayed vault, the translation from Italian to English. And it is a typical vaulted system from the south of Puglia. It is built in situ with few supports and without using of a falsework. Okay, I just stopped to talking about Puglia because I want to talk about the evolution of the fabrication techniques from tradition to robotic. For sure, stone is an ancient material, but its use has evolved over the centuries until to embrace the digital revolution and the last few years, the use of robots as well. And the first phase of this evolution is the traditional era, which has lasted several centuries, as you know. And among all the traditional construction techniques using stone, there is one which is particularly interesting for us, which is stereotomy. I don't know if you know this word. It's a strange word, but stereotomy comes from the Greek and indicates the art of cutting solids. And it is historically related both to timber and stone mostly. And stereotomy derives from medieval cutting stones techniques, which have been evolved to allow the optimization of the voussoirs production and the creation of more complex architectural shapes. And you can see in this picture the vault of the Hotel de Ville d'Arles. And stereotomy is particularly useful when the complexity of the geometry to be constructed needs to control very well the design of the constituent parts of the vaults starting from the design phase. So it's not only a design tool, but it's a way for starting to imagine a new type of architecture. And despite its utility, in order to create such an amazing vaulted space, from the second half of the 18th centuries, we know the progressive disappearance of this of the art of stereotomy from the architectural scene. And this happened mainly due to the introduction of artificial materials and the consequent development of construction techniques and design methodologies appropriate to their use. But the event that changed the recent history of design is the so-called digital turn, which has given the ideal condition to overcome the modern versus postmodern contraposition. And the massive diffusion of computers for design has completely changed the reference paradigms of the discipline, finally allowing for me the development of new architectural languages deriving from new design methods. And also, I think it is important also to update some old techniques like stereotomy. Of course, the realization of this new architecture is allowed by digital fabrication. And starting from the 2000s, architects understood that the information of the digital 3D model could be used directly for manufacturing and construction purposes, thanks to the use of CNC machines and other tools. Anyway, the introduction of digital technology in the stone industry is therefore the result of a long evolutionary process than a real revolution, like in other sector of architecture and fabrication. And this has allowed us to maintain a series of technical and practical know-how deriving from a long secular tradition, which then merged with the innovation brought by digital technology. And as an architect and designer, I've started to think about how taking advantage of these tools and find a way to express their potentialities to update the stone sector. In the same year, the introduction of digital technologies led the development of digital stereotomy, which is the main sector in which I worked, and which is an update of the discipline made possible by the spread of parametric modeling and CAD/CAM fabrication systems. Today, in the scientific literature, the term stereotomy is used in a broader sense because it has partly lost its traditional association with the stone architecture, approaching the literal definition science of cutting solids without any reference to a specific material. And this is what I've called with my supervisor, Giuseppe Falacara, stereotomy 2.0. With him, I've co-edited an entire volume of the Nexus Network Journal about stereotomy 2.0, which included an unfinished manifesto just to stimulate the discussion on this topic. In this text, we studied that stereotomy 2.0 is closely related to the use of digital design and manufacturing tools like robotic arms. And we also stated that stereotomy 2.0, we should investigate the unexpressed possibilities of the discipline and overcome the limitation imposed by individual materials like using just stone without the aid of other materials. And for example, by using composite materials born from the union of materials with different characteristics. I'm very lucky in the last years to collaborate with companies and other designers in the realization of several prototypes and research projects in different fields such as architecture, digital crafting, and industrial design. And for example, in the field of industrial design, I've supported my research group and the company Generali SA, which is a Swiss company specialized in complex stone, marble, and granite processing, and in the design and realization of experimental projects in order to show the new possibilities offered by the use of the robotic tools and also the marble or stone or granite reinforced with carbon fibers. And obviously the carbon fiber is used to absorb tension stresses, and in this way we can make the stone thinner and lighter. This is just an example on what this relatively new field of digital stereotomy and stereotomy 2.0 and new stone use is about. And the fabric, in this case, for example, the fabrication process is based on the freedom permitted by the robotic fabrication and employs vacuum bonding to join carbon fiber layers to thin marble, granite, or stone. The most notable example of this research is the lapella chair, which has been designed by Zadid Code with the support of AKT2, our research group, and realized by Generelli. Due to the free-form shape of the chair, we carved the constituent parts from several small solid blocks, as you can see in these images. And this is just a picture of Lapella's team in New York. Here you can see the results of this small experiment. And moving from that, also from moving in the field of industrial design, another project I worked on is Coral Table that has been exhibited at Marmomac Verona, which is a big stone fair in Italy, in September 2019. It was designed by Dustin White with my support. And for this exhibition, which was based on the naturality of stone, so to highlight the natural aspect of stone and marble, we proposed a large format table design featuring a continuous woven minimal surface geometry, as you can see here, to be fabricated in Palisandro marble. And the shape is inspired by natural phenomena like erosion of the rocks and color reef grown patterns. And we started from a single solid block of Palisandro marble, 3 to 1 meters. And using robotic tools, we cut away some parts of the block by using wire cutting. And after that phase, the robotic arm mill away the marble layer by layer, as you can see in this video. It was a long process, like a digital sculpture, we can say. And final polishing has been done by hand by highly skilled artisans. However, most of the fabrication process has been done by using a robotic arm, as you have seen. And this quick video, okay, was taken during the exhibition in Verona. And I'm excited to show the table because it is a perfect example of blending between robotic and artisanal skills, which is a key aspect of the evolution in stone design and fabrication. The last project that I want to show is a Flux Vault, which is a vaulted pavilion designed in collaboration with Giuseppe Fallacara and the French company SMBR. So we are moving from industrial design to architecture or small scale architecture. And the pavilion has been the representative stand of the SMBR company during Rocalia in 2017 and 19. We presented it 2 times. And Rocalia is the French fair dedicated to natural stone, and it is held in Lyon every 2 years. Flux covers an area of 36 square meters and has a maximum height of about 3 meters and 20 centimeters. And the shape of the structures derives from a base surface formed by a network of catenary curves in such a way to make the vault subjected almost only to compressive stresses. And the key aspect is that the structure is designed to be mounted with the help of very limited support to avoid the use of a timber centering. And also, for this reason, each block is designed to weigh less than 500 kilograms to facilitate assembly and to be produced by using robotic fabrication. And each contact face among the various voussoirs presents a metal fixing system. You can see here. And this system, it is a bolted fastening system placed on the plates at the outer edge of each block. Due to the complexity of the stone blocks to be produced, robotic fabrication is the most appropriate technique to use in this case. And wire cutting has been used to cut the contact faces between the blocks, which are completely flat, while milling has been used for carving the overall shape of the blocks and the sculptural relief. The precision allowed by robotic fabrication is a key aspect of this project, also for its construction, because the details we designed have permitted us to assemble and disassemble the structure in just 2 working days without producing wastes in scaffolding. In fact, each voussoir was lifted from above and temporarily attached to a metal frame placed above the structure, and each stone as positioned, as placed and mechanically fixed to the subsequent ones until the keystone was placed in position. The sculptural relief of the interlocks remembers the flow of internal forces of the structure that proceed from the arch to the ground seamlessly. On the one hand, their present intends to enhance the technical capacity of the latest generation of CNC machining, and on the other hand, they represent a possible way to revamp the sculptural tradition that has always characterized stone architecture, obviously updated in a contemporary way. These are some pictures of the finished pavilion and some details pictures, you can notice the very high precision of robotic manufacturing and the details of the metallic connection between boxes. These are some pictures took during Rocalia in Lyon. And in the initial project, we designed a cup, you can see here in this rendering, to be made of micro concrete by using an additive manufacturing process. However, for budget and time reasons, the top of the vault has not been realized yet. And this is the view. Another option to evolve this research, I think in an interesting way, would be to continue to build the cap by following the contour lines of the structure, as you can see in this picture. But it's a way not investigated yet. Last two pictures I want to show, I've been taking to the Festival Européen de la Pierre 2 years ago at Château de Rohan in Saverne, France. It's I like to show this picture because you can compare two completely different way to use stone in the past and now made possible by using digital technologies. And the last interesting fact to note is that this pavilion is maybe the first example of a reversible and remontable stone vault ever made, because we have used this stand for several fairs, and I think it's an interesting fact for a stone vault. Thanks a lot for your attention. If you have any question, you can ask. Thank you.
Thank you very much, Maurizio. Super interesting, and I'm sure there are some questions and discussion to follow. It's also interesting to see how these two projects were different, but yet connected in terms of how we are dealing with material intelligence, fabrication intelligence, and so on. Okay, to move on, we go to the next presentation with Ginevra Nazari, who is also from Italy, but based in the Netherlands. She has recently earned her cum laude Master of Science degree from the Faculty of Architecture at TU Delft. She also holds a bachelor degree from Roma Tre University in Rome. She's currently a parametric designer in Apto Architects in Amsterdam, and she's going to share her thesis project with us called Remote Reuse, Plastic and Robotic Modification. Ginevra, you may start.
Okay, good afternoon. My research project is called Remote. That stands for Reuse Plastic and Robotic Modification. Reuse plastic because everybody knows that plastic, because they're widely used and now they're fundamental for the global world economy, but they're also one of the biggest environmental issues nowadays. That's why it became really necessary to start to recycle or reuse the plastic products. At the same time, we're in the middle of the fourth technology advancement. So the question is not anymore if robotic production will be used in the building process, but how it will be used. This brings me to my problem statement, that is, how can computational design and robotic production help to reuse plastic in architecture? To answer this question, the research process was divided in 3 parts. The first part was about the research design. The second part was about mainly the fabrication. And the third part was the design of the pavilion itself. That is the final product of the research. So starting from the research design, the starting point of the research was to look for a plastic object that could be used for the design of the pavilion. So many plastic objects were selected and tested. And at the end, the selected object is the one that you can see in the image, which is a hollow and openable plastic object that it's usually used to store and transport drilling heads, but that when it reaches the destination is just thrown away. So it will be destined to the landfill. So starting from that object, the main design concept is to take advantage of the flat base of the component in order to create junction elements based on the repetition of the component. So in the image you see like a 6-component junction, which is way too much, but yeah, that's the general concept. But at the same time, to still allow freedom and complexity in the design, a computational system was developed. And it's based, of course, on different steps. The first step, which is step 0, is the initial surface, which is like the shape of the pavilion, which can be whatever surface. Then this surface will be tessellated. I'm not sure if you can see it, but so it's usually tessellated in hexagon and pentagons. And at the edge of the tessellation, the joints based on these recycled plastic, reused plastic elements are placed at the edge of the tessellation. And consequently, a ribbon structure is also created, which is also based on reused plastic PVC pipes. And the last step is the covering the pavilion with some textile that is also reused. So going into the fabrication process, it started from the extraction of this joint from the computational system. So the advantage of using a robot is that every joint is different from the other. So it was easier to create a robotic toolpath, of course, than doing manually. So the fabrication process was based on the idea of removing of taking one component and removing a part, and on one side, and on the other side, the plastic itself of the component was folded and used as a connection material itself, in order to don't use any other material and to don't create waste. So the fabrication process is based on 4 steps. The first step is the cutting of the component with the robot. The second step is the folding of the plastic with a heat gun. The third step is the gluing of the washer, and the fourth is the connection of the parts to each other. So now there is a video regarding the simulation. I hope you can see it. This is the simulation of the robotic toolpath. So you can see how the robot is cutting the component, and this is the actual oops, sorry for the sound. So here you can see that the robot is actually first drilling the holes in the component that will be used for the connection of the components to each other, and then is actually removing the material which is not needed. Oh. Yeah. Oh no. And this is the last step of the fabrication process. So you can see that actually the parts that will be used as a connection between the components are folded with a heat gun. Of course, they are folded at the right angle so that they fit perfectly into each other. So now you see actually that the component fits perfectly into each other. Yeah. So this is the final prototype next to the 3D model. And it was also structurally tested in order to understand the strength of the prototype itself. So this is the final prototype, which is a portion of the final pavilion, and is based on, as you can see, on the repetition of 5 plastic joints, which are connected with PVC pipes, reused PVC pipes, and it's covered with a reused textile. So for the last step, that is the pavilion design. This is the final result, which I hope you can see. So yeah, this is the pavilion that is based on the repetition of these hexagon and pentagons. The video is actually a bit weird. Yeah, so this is the pavilion in the location, and you can see the joints based on the reused plastic object, and again. Oh. This is the pavilion placed in the location, that is the TU Delft campus. And to conclude, this is an approach on how the robotic assembly could be implemented in order to reduce the manual input, because of course there was a lot of manual input because the components were connected to each other manually with a rivet gun, but the whole process could be automated in a way to reduce the manual input. So in the original configuration, the object was fixed and the robot was moving around it, but an hypothetical improvement could be that the robot is equipped with a gripper and is moving the object in front of the milling tools in order to implement the whole process. Then the same robot equipped with a gripper can move the component in front of a heat gun. And the last 2 steps could be implemented in a multi-robot setup with 2 robots. So where one robot is equipped with a gripper and the other robot is folding the plastic. And the last step is the assembly where one robot is keeping the component and the other robot is bolting the components together. Yeah, thank you.
Thank you very much, Ginevra. Interesting to see how robotic fabrication can sort of extend the material palette, and also how we can question the existing architectural education, let's say, paradigms. So to move on, we go to the first presentation by Giulio Rugnaro. Giulio is a trained architect, designer, and researcher working in the field of Industry 4.0, robotic fabrication, and applied machine learning for design to robotic production workflows. He has been a Marie Curie fellow researcher and PhD candidate at UCL Bartlett. You founded InnoChain Research Network program. Giulio holds a bachelor degree from University of Venice and a Master of Science from iTech program at University of Stuttgart. He has also been a teaching fellow of MArch Design for Manufacture program at UCL. Giulio, you may start.
Yeah, okay. Can you hear me now?
Okay. Yeah.
All right. Hey, yeah, thank you so much for giving me the opportunity to present my work. I'm really excited. So you already presented you already gave my presentation, so I guess I can jump straight into the topics. The title of the presentation today is Robotic Training for the Integration of Material Performances in Timber Manufacturing, which is a long title, however, which hides behind actually an even longer research I've done during the last years at the Bartlett School of Architecture in London as part of, as you mentioned, the European funded research network called InnoChain, which basically brought together academic institutions across Europe together with industry partners to collaborate together and develop projects which were both relevant for the academic and industry discourse. And in the specific, my two industry partners I collaborated with are ROK Architects in Zurich and Big Bjerginges Group in Copenhagen. So focusing on timber robotic manufacturing and subtractive manufacturing, actually, the research investigates a series of robotic training methods for the synthesis and integration of manufacturing knowledge at an early stage of the design process to enable the exploration of novel design opportunities informed by tools and material affordances. So in current design practices, the lack of feedback information between the stages of design and fabrication forces designers to engage with only a limited range of standard industrial materials and manufacturing techniques, which leads oftentimes to wasteful and inefficient solutions. So one of the main issues hindering the adoption of heterogeneous material is the large deviation between what is prescribed in a digital design environment and the fabrication outcome, which is basically caused by the variance of their material properties. So this is particularly detrimental for the use of a natural heterogeneous material such as timber, as it needs to be homogenized before becoming suitable for a conventional manufacturing environment, oftentimes requiring heavy industrial processing and material waste. So while craftsmen establish a direct dialogue with the material through direct exchange of feedback information, designers who do not have access to this type of knowledge need to find alternative ways to include the affordances of material as part of their design process. So the creation of material hypotheses in a form of digital models which are tested within a simulation environment appears to be a promising strategy to receive valuable figure information before actually moving to the production stage. However, the acquisition and integration of manufacturing and material knowledge necessary to validate the simulation framework has emerged as one of the main bottlenecks in the development of material interfaces that would enable designers to engage with the affordances of production processes. So to address this issue, three main opportunities have been identified from the fields of manufacturing and computational sciences. Firstly, the recording of a skilled human expert to extract their tacit knowledge and use it to model a wide variety of robotic fabrication tasks. Secondly, the adoption of machine learning models to synthesize knowledge from large fabrication datasets collected through sensor devices to support decision-making in the field of manufacturing. And thirdly, from design workflow of metal components, the evaluation of design instances through automated manufacturability feedback supported by a simulation framework and a knowledge base. So based on the literature review findings, the investigation has been organized around a technology-led and a design-led component with their two different respective methodologies. The technology-led component focused on testing the nature of the material variance of timber and the extent to which it's possible to predict its influence on the geometrical outcome of robotic carving operations. The design-led component, on the other hand, addresses the integration of the development methods in the workflow of design firm and its implication in the evaluation of design solutions. So the first stage of the training methods concern the acquisition of real-world fabrication data and its processing into structured data sets for the training process. The device sensing strategy for the recording of carving operations makes use of two main techniques: motion capture cameras and photogrammetric reconstruction. The system of motion capture cameras, as you can see in this video, is used to track with high degree of precision the position of reflective markers in the recording space and reconstruct in real time the fabrication tool, also in the digital design environment. So after the carving session, each training board is reconstructed as a 3D mesh through photogrammetry and segmented to isolate and analyze individual operations. These techniques combined makes possible to successfully reconstruct each operation to a high level of details necessary to measure the variance level within a range suitable for design applications. So the integration of an initial human demonstration of the task together with the data acquisition recording performed with industrial robotic arm is here particularly beneficial, as it makes possible to narrow down the mapping of the parameter space and avoid dangerous or inefficient operations. So the design of experiment approach, guided by the human demonstration, made possible to efficiently structuring the data acquisition and demonstrating that properties such as of the materials, such as the wood grain arrangement, density, and species, basically determine a deviation between the digitally prescribed operation and its physical outcome, which results substantially above the tolerance threshold sufficient for design purposes. So the human demonstration data in black provide a safe subset of the 4-meter space as a starting point for the robotic exploration in gray. The initially defined boundaries are gradually extended during the robotic exploration with the aim of building a more comprehensive understanding of the fabrication task and increasing the prediction of the performance of the system, providing a larger amount of data. As a consequence, unlike in the human dataset, robotically generated dataset will consist of both successful in red and unsuccessful operations in blue, depending on specific user-defined criteria. For instance, when it's not possible to extract the tool from the wooden board, or the opposite, when the operation doesn't actually remove any material volume. So the modeling of the influence of material properties to robotic carving operation has been addressed through a series of inductive methods based on the training of supervised machine learning models aimed to identify patterns in the recorded fabrication datasets. The training workflow is organized and presented actually here in two main sections. The first component is a binary classifier for the prediction of manufacturing conditions, which shows that it's possible to predict with high accuracy whether a set of fabrication parameters will generate a successful or unsuccessful operation according to a set of evaluation criteria defined by the user. The second component instead is focused on the prediction of the geometric features of carving operation after being filtered by the binary classifier. The results here shows that the artificial neural network trained with the real-world fabrication data are able to actually map between robotic fabrication toolpath to carved geometries with a low error rate below 1 millimeter, making the simulation tool actually suitable for design purposes. So models trained on different fabrication conditions are particularly sensitive to material properties, wood species, and tool specification, and enable the parallel evaluation of the influence of different fabrication configuration on the desired outcome. So the testing of the device strategy within actual design workflows was addressed through a series of case studies performed in collaboration with the industry partner in the project, ROK Architects in Zurich and BIG in Copenhagen. Each industry collaboration unfolded in an extended catalog of robotically fabricated components and multiple digital design iterations supported by the simulation tool, which has been trained by the team of designers to fit every time the specific scope of the design brief. So the device workflow entailed a sequence of what-if analysis evaluating the influence of geometric pattern variation, wood species, density, grain direction, carving tools, and specific fabrication parameters, which substantially affect the resulting geometric features of carving operations. So the design outcomes have been every time reached only following a multi-step design process where the designer has been asked to make critical decisions based on a material and fabrication simulation provided by the trained system, unlocking this way a range of design solutions which would be otherwise unavailable in a purely digital environment. So the final stage of the exploration is the robotic fabrication of a series of card panels, which results from the sequence of what-if scenario examined by the design team. For validation purposes, each fabricated panel is digitally reconstructed through photogrammetry, as we've seen before, and compared to the predicted geometry through the analysis of the deviation between the two, which is visualized here as a gradient color mapping. So the main contribution of the research is to the field of robotic manufacturing and digital design interfaces, as it focuses on utilizing sensor data to train material-sensitive fabrication systems and integrating them as part of design workflows. So although the research strategically focused on a specific application, such as robotic carving with timber, The developed methods have here the potential to be applied to a broader variety of non-trivial robotic manufacturing tasks requiring high-level understanding of the process and the affordances involved. Part of the novelty of the approach is in this, of the approach proposed in this research lies in transposing established methods for the field for optimizing robotic manufacturing from the industrial manufacturing sector into the workflow of creative practices to augment and support the ability of designers and to provide feedback information to guide the design process. So the successful development of a series of methods to collect, process, and encapsulate manufacturing knowledge and its application within a design environment fundamentally demonstrate that the benefits of interacting at an early stage with the fabrication tools and material furnaces to make better informed design decisions and enable this way the exploration of a novel range of design opportunities and solutions which would be otherwise unavailable. So thank you for listening. I'm happy to answer any question later and looking forward for this discussion.
Thank you very much, Giulio. Really interesting. It shows how integrated computational design and robotic fabrication techniques basically open up new doors for material computation. We're gonna come back to this later. To finish the presentations today, we move to the last presentation by Tristan Gobin. Tristan Gobin is the Director and VP of Construction Automation at HAL Robotics. Graduated with distinction from MArch program at ENSA Paris Malaquais. Tristan has led several robotic workshops at ENSA Paris Malaquais and the UCL Bartlett. He's now a PhD candidate at Graduate School of Architecture at ENSA, and he's also a part of research building project at National Advanced Civil Engineering School and the Navier Laboratory at École de Pont, Paris Tech. Tristan, you may share your presentation and start. I think we don't have a voice yet. Yeah.
That's good. Okay. Good afternoon, everyone. So thank you for the introduction and to invite me here. This presentation will be actually a collection of several experimentation and development that we do in our robotics, but with a starting point from my own research when I actually start my PhD. So, oops. So, well, the first thing is I start from a design perspective as a trained architect, but then I moved during the PhD, and also because I start HAL Robotics with 3 other guys, Thibaut, Sebastian, and Remy, and I start looking into the robotic aspect of things, not from the design. So in 5 years, I kind of lose my not the interest, but I'm becoming more away from the design, and I'm more on the side of developing tools for designer actually. So what you are looking at is well, the diploma. So it's like 5 years ago, and it was about how we can use robots to operate on site to constrain structure. And actually it led to a question that was, can we reach on-site robotics operation? Is it possible? It's can we do it? And to do it, what is necessary to develop? So my presentation will be separated in 3 categories, and I will try to summarize through case studies the 3 main approach that we have in robotics, and actually we need all those 3 approach to maybe achieve some days robotics operation on site. So I would say that to separate these strategies is actually, from our point of view, as developers of tools for robotics and to control machines, it's a lot about programming strategies and how we interact with the machines. So first, you have the explicit control of robots. You basically do some codes without knowing the context. Is exactly the opposite of the previous presentation, actually, because you don't have a clue of how the material behaves. You don't add sensors. You have no information, no feedback from the environment. But it's the fairly known and the most common way to use robots. Then you have the adaptive sensors. Well, we had an example before, and actually it's one of the main use of robots is to have sensors for sensor and other things to adapt the explicit programming to specific variation that you can use to avoid collision, avoid to burn the materials and this kind of thing. And then you have the collaborative aspects, where you have skilled humans that start to interact with robots through sensors, and you have a global system. And actually, we need that to have operation on site, and I will go in details on that later. Well, I will talk about several case studies, but it's to summarize one of the main ones. We work on different and with several entities. Let's say we had the opportunity to work with CETA, we work with Laboratoire Navier, with X3 also for 3D printing. And yeah, well, I think some of you guys know some of those projects. I won't be going into details into that. And well, the approach here is to show you that we have this, well, for the moment is the development we reached. And I would like to go into detail on what this development means and like program level. So what we're trying to do is to link, obviously, what we have as designer, what designer have as tools, where Rhino, everything that can be used to design things in on computers, and then you have to link this to the real action that will do the robots. And for that, you need a whole environment to link everything. When you start to explicit programming, I had the opportunity with the Ponts des Chaussées to try fabrication on wood. And the main reason we started to work on that, it was a two-step project. We are at the second steps, but I will show you the first one, which is how can we work on fabrication and have the capacity to use a robotic cell to fabricate things and then to assemble them. I'll show you the first step. Go for this detail there because I don't have that much time. But just to summarize, we had these teams on this project. We worked with Simona, Ponts des Chaussées, Wurt for the screws and stuff, ABB for the robot, and Schunk for the gripping system. So we built this this structure, and it was a vault basically, and we tried to achieve a quite complex structure, but actually the thing is we tried to avoid complexity on nodes, and that was the base, the starting point of this study. We tried to avoid complexity on nodes, so we worked on next-array structures, which avoid actually having too much connection order, and to remain for the beams that you have here, you just have a beam is connected to the end to just one beam. So the detail is not that complicated. But then the problem comes from now to adapt the geometry, because it was a curved surface geometry, And to allow us to do that, we had to try to embed in the beam all the complexity that came from the surface. So I will we end up to a specific specific workflow, and because we had to link the design of the geometry, the several details like the screw position, the how the beam geometry will be fabricated, and also the structural analysis. So we have this workflow. We have those components, and actually the beam itself summarize a lot of the complexity, because in this beam components we had the screw, we had the turn-on and mortise, and also the panel slots the slot for the panels, and those complexity to achieve a certain smoothness in the surface, and also to make sure that the screw were not colliding together. Well, it was a work that embed the fabrication constraints and the structural constraints, and those things were looping to make sure that we achieved something that was actually working with all the fabrication constraints. I'll show you an example of the cell workflow. We had two robots, one picking the beam, some cutting and milling operation, and drilling operation. So you have these first steps which is the picking. It allows us to, and we actually did that without any sensor. So it's really basic way of doing things. But if you are well organized and smart enough to order the operation in the right order, let's say, then you don't sometimes you don't need to calibrate everything. For instance, here the cutting allows us to know the precise size of the beam, and also we know now this in terms of positioning in the space of the robot. We know how to interact with the beam because we already cut it in a known space, which is the space of the robot. So we have this operation, and then once everything is done, you have the drilling for the screw, and we actually get the opportunity with this to experiment with several tools, the static tools and the embedded tools on robots, and how we can have a global cell. And but the real interesting thing in that, it was because all the beam were different, we had to optimize a lot of things. For instance, we had to, because of the size of the beam, we had to move slightly the position of the beam according to for one of the robots, because of the reachability of one of the robots. And also we had to take in consideration the collision between the tools. So this was, we had to optimize that. So for instance, we had this several operations to make sure that the turn-on and the mortise, and each time we make the mortise, there is no collision between the tool and the gripper, the milling hand and the gripper, and also for the surface of the beam. So this is basically a process without knowing, without having any feedbacks. But then here we had to optimize everything. So that's, let's say, the first steps. By the way, it was also designed, the beam were designed to be movable by one human or two, and to make sure that we can build it without any problems. So this is a nice pictures of no snow, not snowing that much in Paris. So, well, it's nice to see that. Then it comes to the adaptive programming. So now it's about how you can embed the information that can come from sensors and to kind of evolve the programs that you explicitly do. And then you want to, for instance, adapt from force sensors on laser distances, etc., the behavior of the robot. So there were several examples about that before, but I would say that our problem here is that we doesn't want just to adapt a specific tools, but we want to have a global framework that can embed every type of operation. And that means we need, for instance, for us, this is the same operation, which is something that maybe you know, it's kind of old now. And well, the thing is, for us now, this kind of operation, we try to generalize them. And for us, it's kind of the same thing. We basically try to have information coming from the sensors, and we have a pipeline in the framework that allow us to embed this kind of information and interact with the robots and make them act. If it's force sensors, motion captures, whatever, it's actually the same pipeline that should be used, and is for us the most difficult part to achieve actually. But then it will be help us to manage to put machines on site, because as you know, it's quite a mess. A construction site, it's quite a mess. You have a lot of actors, and you want to be sure that every machines and people, etc., interact properly. Which led me to the last part of this, which is the collaborative programming, which is something that is the most difficult to achieve. You may have heard about cobots and stuff like that. We are at the beginning of that, obviously, and there is a lot of leads to follow to enhance this interaction. For instance, one of my partners have the opportunity to work on how you can control robots by speaking to them, and it's one of the I think interesting proposition. And also the really important thing here is that some operation like the one you see here are quite difficult, not impossible, but quite difficult to numerize, let's say, to digitalize, sorry, because it's really linked to a very, very specific huge knowledge that not so much people know actually. In this case, bending glass is really hard because you have to know the perfect temperatures, and actually it's also hard to have proper sensors that are capable of and have enough accuracy to get the exact moment where you can bend the glass without breaking it. So in this situation, it was the guy was like asking to the robot to move at the good moment, and but it's old elements. So I think you don't have the sound, but it's not a problem. It's just like Sebastian is like here asking to the robot to take a break, and then there is this interpretation using other frameworks like the one that can be provided by Google, or the one you can have when you in your telephone when you ask Siri or whatever to interpret your words. And that's also the point. We can use a lot of library that actually already exists to enhance the capacity of the robot. So it comes again to the question of the pipeline, how you link everything. You may have also saw that it's how we can interact smoothly with sensors. In this case, it's a leap, get the position of the end. And here to have also the interpretation of if the hand is open or closed to activate the gripper or not. So it seems to be quite fun here, and actually it's development, and but for us it's really the starting point of what we will be capable of doing on construction site. So we are always experimenting on enhancing the tools that we have to allow us to reach this objective. So the last 2 years, we have one achievement about that, was the building of the first version of a platform. I don't have the right to show the second version of this platform, but we are working on it, and now it will be industrialized and commercialized actually. And it's a platform, it doesn't look to that anymore, it's a bit more industrial in the design, and it will be used to operate on site, to drill, to make drilling operation, and especially when you have a lot of drill, to make sure that you can also get the information where you drill to make it back into the BIM model. So this whole approach is, well, the last year of development. It's a continuing development, and well, I don't spend too much time in this video. It's just to have a glimpse of what we are developing. And I will conclude by something that, well, the last development we are doing actually, well, we are trying to embed systems, so move from, you know, the environment of Grasshopper and Rhino, and move our framework, etc., on Raspberry Pi and microchips to allow us to control a lot of things, sensors, etc., cameras, and blah blah blah, to make sure that we can interact with a lot of things. And for instance, we work on several various
Tristan, we have lost your voice, I guess. Hello. I think we have lost your voice. Do you hear me? No, we don't hear you. Maybe. Okay, you do hear me, but can you talk now? Because I guess we don't hear you. Or can someone else talk? Maybe there's something else.
Yeah, I cannot hear either.
Okay, so you hear me, but not Tristan,
yes.
Right?
I think everybody can hear. It's just Tristan's microphone that might have some issue.
Okay, maybe. Tristan, maybe your microphone has switched to another type of microphone. If you go to that little cursor, the icon of mic, and change the select a microphone, maybe that will sort of activate your microphone back. Maybe you can restart.
Under mute or unmute, there's a, if you can go there and click on that, and it gives you a list.
Hello.
Do you hear me now?
Yeah, we do hear you.
Yes.
I had
Okay.
to restart Zoom actually. I don't know why.
Okay, so maybe you can start over again, probably where you were discussing this talking with the robot platform. Yeah.
Here?
Okay, go on.
Okay, so I was I was talking about how we started to embed what we developed previously into one platform, let's say. So this is the first version. I cannot show you the last one, which is a new developed second edition, I would say, more industrial and robust. This one was more proof of concept. And we are working with actually everything that we developed. You can see on these pictures the motion tracking system that know where the platform is. We have various sensors around, and everything is talking together. And also when the robot is operating on the site, for instance, when you have to drill somewhere, it will communicate the real position where the machine drilled, and upload this information to the BIM model to have perfect links between. For instance, when we work on a specific operation, when you have to drill a concrete slab with steel inside, and you want to avoid where the steel is, well, you detect where the steel bar is, and you move a bit away, and you upload this new position to the BIM model to say, hey, this screw hole is actually a bit on side that it was previously asked on the plane. So we are actually working on this kind of thing now. I won't go too much into detail in this video. It's just to show you the platform. But as you see, there is various sensor on it, and it's just for the moment is, well, for this kind of operation, but it will be used for others because you can swap tools on this robot, so you can have scanning operation, tooling, drilling, etc. And so to conclude on that, what we try to do is to go more into embedded systems, like to embed our framework into microcontroller like Raspberry Pi, this kind of thing, or Arduino maybe. Not exactly the same, but we are aiming to develop more elements for small and embedded systems. We try to also develop various approach for different type of processes. We are going into welding, milling for wood, on 3D printing, this kind of thing. And we try to work with the guys that are actually knowing how to do that, because we are not a specialist of welding, etc. So we try to develop as much as possible dedicated system for specific work environment and specific people. And we also had the opportunity to embed our system in some robots, work on modular robotics. So it's an interesting concept that allowed to swap some part of the robots and to modify the range and the motors also, so the weight and the capabilities to hold heavier or lighter tools, etc. And then we try to work on also augmented reality, again, to make sure that we loop everything. We can have a link in between everything. And yeah, that's the last development, I would say. And I will be done on that. Thank you.
Thank you very much, Tristan. Super interesting. It is really interesting to see how robotics has been focused on processes and workflows. And also, you also touch upon a very important topic, which is assembly, which is how we can go beyond the production space of any specific robotic production setup. Okay, with this, we close our presentations and open the panel discussion. So we invite everyone to join the panel session. I guess we may have some questions in the chat box, but we can first open the floor to our committee. Maybe you would like to ask some questions.
Okay, yeah, could I ask the question, Sina?
Sure.
So anyway, thanks for the great presentations. I mean, I really enjoyed today's presentations, and especially the Italian Mafia. Just to say, I actually have a background in Italian Mafia because I translated Alberti. And the question of ornament and structure was alluded to is not just Gothic; it refers to also to Brunelleschi and Alberti and those two figures at the beginning of the Renaissance. But I had a question though for Ernesto. I mean, stone itself, I guess it's not completely homogeneous. It maybe has certain kind of structural fault lines and so on, which I guess could be addressed or incorporated in your research. The second question was kind of related in some way. Is when you on your vault, you had these kind of striated lines. They seem to be ornamental. I mean, they were. I think you said it was. They were expressing the structure, but the word or representing the structure. So the question would be whether those striated lines were actually structural lines. I'm comparing it to somehow to Philippe Bloch's work, and I was always struck by the way that his kind of structural lines in his work, especially that 3D printed floor slab he did. It reminded me of the way that, for example, King's College Chapel, the fan vaulting works, which is very, very beautiful. But I didn't see those structural, those striated lines as being continuous. I couldn't see how they were operating structurally. Were they merely representing structure, or were they actually a kind of ornament that was structural?
Maurizio, you're muted.
Oh, sorry. Can you hear me?
Yes.
Yes.
Okay. I was saying I think the second. I think that our intention was to make a sculptural ornament, a sculptural relief that shows the way of the internal forces flow from the top to the base, to the ground. So, but it's like a needed representation of these forces. It's not how to say scientific. Obviously, it is based on the behavior of the structure, but it's not so scientific. Our intention it was to how to say make our intention was to show that it was a load-bearing structure. Okay, so the stone was used in a load-bearing way. Not and also we were interested in show the potential how to say what can we make with robotic fabrication. Okay. But also related to stone culture. It was our intention.
I just think it might have been, I mean, I love the project, but it might have been even stronger if it had been able to literally express the structural forces rather than represent them. I don't know, I just, but anyways, it was beautiful to see your work because there was a tradition, I think it comes out of Italian stonemasons going through into contemporary digital fabrication. Anyway, thank you.
Thank you. Thank you.
Yeah. I think that's a very really relevant question, Neil. This idea of ornament and how with digital fabrication we are able to produce ornaments. I think one question is that how we can benefit this ornament. For instance, we see in the lecture by Ashish that the ornament was sort of a performative solution for certain performance requirements. But at the same time, I think it is important to be able to produce complex forms. Then later, maybe not in one project, we would like to solve all the problems. Then later in another project, because we are able to produce such complex forms, we may be able, we might be able to sort of implement this in another context. And something that maybe Ashish can pick up, because we saw a very interesting implementation of ornaments, which sort of integrated in the computational design workflow. Ashish, you might want to add some comments about that.
Yeah, because the question is again about authorship, right? So let's say like 5 of us have the same robot, 5 of us have like the same geometry and same printing head. And then if we print the same object, what is the authorship? So like that's what my point was here. So that the process, if you can manipulate the process, the nodality, like how architects used to make drawings, here we are making the nodes, right? The code for the robot. So there we can actually put something of your own, your tacit knowledge, which is there, what you have learned, and you can put it in that code, and then it becomes personal. So like even like the Ruskin's argument of ornament, that it comes from the error of the human hand, right? That every object is different. So here, by this kind of node which we create in the code itself, then every object could have this kind of own authorship and this kind of own ornament. And that was the point I was trying to make.
Exactly. Great. We have some questions from the audience addressing the work of Julio. It's asking, I was wondering if you have investigated the effect of the curved texture on the thermal properties of aerodynamic aspect of the fabricated artifacts. So maybe you can up on this, and there are also other questions that I have for you, Julio.
All right, I can start from this one. I haven't actually. For sure, there is a performative aspect that can be associated to the design and fabrication of these kind of like complex surfaces, right? But that was kind of outside the scope of the research, but that's definitely a potential way of further developing, where instead of actually developing and assigning a formal outcome, you define a performance goal, and then you come up with a computational strategy that, using the tools that have been trained and which are aware of the affordances of the materials and tools, can actually be steered toward that outcome. So I think that's definitely like one of the interesting aspects, moving toward a more performative dimension of the formal outcome of the carving operation.
Great. One question before maybe we move to other questions. It is interesting to see how developing a new tools also question maybe known manufacturing processes like subtractive CNC processes. So I wonder if you have been sort of investigating or comparing this method of fabrication which you have developed to some existing method of fabrications, and if you could sort of draw some conclusions regarding this comparison.
Yeah, so that's actually been a recurring question during my research. How does this compare to more established techniques such as, for instance, CNC milling and so on? And I would say, like what I always try to focus is actually not necessarily a parallel comparison, like a direct comparison between, milling versus carving versus using, other type of tool like orthogonal cutting tools such as, axes and so on. The interesting thing for me to compare is the different way these tools are used within design to manufacture workflows, in a sense that CNC milling is it perfectly fits within like a linear process of design to manufacture, where you design an object in your digital design environment, and then you expect the milling machine to actually fully reproduce in that the digital object to a level of precision which matches the notation, but at the same time, at the same time overriding completely the agency of the material. So therefore, you don't need to worry about whatever happens in the fabrication stage, you know, that the notation will match with the physical outcome. And that's interesting because in that sense, the other tools, such as, for instance, the one exploring the research, like the carving tools, actually are not really able to fully override the agency of material, right? They receive an impact from the material. And that's the interesting moment where you understand actually it's not a matter of the property of the material or the tool, but it's a relational, and that's why the terms of affordance is so important in my research, because it's affordance in a sense, as the definition given by Gibson, is the set of action that a system can allow to be performed by an agent, and that implies relationship. So, and that's why I actually focus on tools which were not able to fully override the agency of the material, and therefore were prone to be exploring other ways which would require to integrate the affordances of the material early on the design stage. So they cannot be ignored and they cannot be overridden. And so that's why that's how I try to compare the two, rather than, you know, having, you know, there are different tools and different type also of cutting action. So I'm more interested in the way the two different tools are applied within workflows, design workflows.
Can I just say that Julio, I think we had a little discussion, I mean, about that with Akim. Akim always talks about affordances, and I think this is a really, really important term. I know it's a very theoretical term, but when you're dealing with materials, the affordances of materials are absolutely crucial. So I think those who are not familiar with it, it's basically what you can do with certain materials, but it's a kind of a long theoretical discussion about it. And it's a constraint I think we always have to think about. And I really appreciate that theoretical edge that you're bringing into it. I know it comes from Akim. Akim always impresses me. He uses some of these theoretical terms in a very interesting way.
Maybe following that, I think, hi guys, thank you so much for your great contributions and the interesting projects. And I thought it was really interesting that many of you kind of took on the challenge to work with natural heterogeneous materials instead of homogeneous synthetic materials, and really kind of took on that, you know, setting up and basically teaching yourself and teaching the tools to read matter in a way. I mean, it kind of goes along with the affordances, right? And I thought it was really interesting. So for Maurizio, you know, the kind of veins that are in marble that make it a lot more difficult to work with a material like that, I think sets up a challenge, and it also takes a lot more time to kind of set up these processes. And so my question is, do you think, you know, the appreciation for it and the perception of material agency can be something that can be brought into design and kind of contribute, because it kind of slows down the process of working with these materials? But do you think, you know, your work can actually contribute to bringing the appreciation and perception of that slowness into a larger design community? Because I kind of hope so, but you know, what's your feedback? What do you get from people when they see the process takes very long, but it's so beautiful as an outcome? Maybe you can kind of say something to that.
Are you talking about the length of the process in terms of,
yeah,
or in terms
of like something very, you know, if you set up a synthetic material, and you know, it can be beautiful too, but there's something in the marble that kind of is very different, but it takes longer time because it's a heterogeneous material, it's a natural material. So my question is, what's the feedback that you get from designers and maybe just people that see that table and you tell them about the process taking that long, is there, I mean, my hope is that we can implement these kinds of tools more, because I think it takes longer time, but the outcome is beautiful. So I think, my question is just, can that be something that people appreciate more? Do you think there's a challenge in that,
I think that especially in the stone and marble sector, in the last few years, maybe almost a decade, the introduction of these tools, of CNC tools and robotic fabrication tools, also from the design side, design tools, has allowed a creation of how to say, a new sensibility, a new appreciation for the natural materials, and also for, in fact, the table was done for an exhibition, which the focus was the naturality of stone. So because we are in a historical era, we have a lot of materials that imitate stone. So we have ceramic materials, etc. But our focus was on that kind of table with all the veins, all the stone sedimentation patterns, because we want to show the uniqueness of stone and marble. So we developed that shape first to show this kind of uniqueness, and also to highlight the new possibilities that we have using the new tools. And you mentioned the length of the process, but if you think that without CNC machines and without robotic fabrication, in the past we work on stone by hands, I think we had now the possibility to make the stone industry more competitive, because using this kind of tools we can reduce the time of production also, and we can also be more precise. We can produce elements. If you think about customized prefabricated elements for architecture, we can produce them with lower time and more precision. So I think that these tools are opening up new possibilities also for this kind of materials, because that for sure is an ancient material, is not new material, but we can start to think, to rethink it, and to make it new again. I think the same is also for timber, for wood. Also, timber and wood are natural materials and are ancient, like stone. This is why I particularly appreciate the Julius research, because I was saying it. I appreciate it for the relationship between manual fabrication and robotic fabrication. I think this is a new perspective. There is actually there is a debate on the possibilities that that robots and can how to say, make humans not necessary. I don't think so. I think that in the future there will be a strict interaction between robots and humans. So that's why I like a lot his research, because he is working in this direction, and he highlights this perspective.
Maybe I can pick up on that, Mauricio. There's also a question from the audience. Farinaz is asking, your design was awesome. Thank you for sharing. However, did you think about the amount of waste? A massive amount of stone has to be destroyed to have such a design? I think that's a relevant question, but at the same time, maybe before you sort of reflect on that, maybe using robotic production or digital fabrication also question the way we sort of standardize our raw input material, because in many cases we, for instance, receive a block of material or a board of material, while this can be different. So I would like you to sort of reflect on that, and maybe also answer the question by the audience about the waste.
Yeah, I have two possible answers. So the first answer is that the stone sector is not ready, but I think in the future we have to think about how to reuse this kind of waste, because in all the subtractive process, fabrication processes, we have waste. And I think that especially for the stone sector, we can start to think to use this kind of way, for example, in additive manufacturing processes. So we can use them for 3D printing, for example. Okay, so we can rethink also the use of the waste. And the second answer is that, yeah, I know that stone is not stone marble is not a renewable material, but I think that the problem is what you do with the material, with the raw material. If you obtain an object or obtain an architecture or obtain something that produce wastes, but also produce beauty and also produce an added value for the object, I think it's not a crime to use them. Okay, so this is also how to say, this is we can produce wastes for maybe all the human activities. Okay, so it's the same for stone. Well, the problem is what we do, what we want to achieve by using natural resources. And sorry?
Now, one thing that now that you mentioned this idea of beauty, because I can see that there is like a general aesthetic of the unfinished things, no? In all the presentations, you have like a kind of aesthetic of the unfinished. That's why we refer more like to process, or even the Ashinish presentation about certain lack of control. So this idea of the unexpected or emergent beauties that we didn't expect at the beginning of the process. I think that this is important in the way you record this, or you take a register of these unexpected things. So my question is directed to this: how do you record this if you can open the process through these lines, no? Through this line of the emergent, unexpected, could be ornamental, even could be a structure as well. So I want to open the discussion to how you can open your researches to new ways to develop a design, no? Through this kind of lines that the failures, or yes, the emergent open.
Yeah, I don't know really, but I also think that there are maybe other designers, other researchers that have worked with this topic, the unfinished. If I understood well your question, and no.
Yes.
Yes, there are several examples of unfinished. Also in the past, in the sculpture, for example, Michelangelo worked on the unfinished, because I think is an interesting topic for stone, because stone is in nature is unfinished. It's rock. Oh, it's not perfect. So it's an interesting topic, and there are projects that I've worked with this topic. I can mention a building in London. I don't know if you have seen it. They have it is formed by raw blocks of big raw blocks of stone, and they worked on the unfinished pattern of the stone. Maybe I can link it on the discussion on the chat. For me, the problem is that I've always worked with stonemasons and artisans. They want to achieve perfection in the sense of their discipline. So they want to polish the stone. They want to how to say, to clean it. So this is probably this is the why we do not work in this direction for the moment.
Yeah, no, but my idea, I mean, my question was more directed. For example, I don't know, in Ashish processes, you have like this failure. So I suppose that you, I don't know, you create your test records about the failures, or you take notes, or even you can develop like new drawings about the failure. So it can open your design to new designs. So my question was more directed with this, not about the idea of unfinished, like in the history or in other buildings, more in your own researchers. How can this researcher and this PhD researcher with our really incredible and super interesting, how this can open a new field to new researchers for you? I mean, for your work in in the future.
Yeah, I don't know really. I have to reflect about it. I don't know.
Yeah.
Great. I think.
Well, I just wanted to say thank you very much.
Yeah.
Sorry about that, Sina. But Ginevra and I have been having a side conversation that is relevant to what we're talking about, and maybe she can speak a little bit about about Marina's question. I'm not putting you on the spot. I just, you know, you're very interesting. So why don't you start?
I'm muted. Okay, sorry, but can you repeat the question? Because Gustavo was writing me a lot, so it was difficult to keep up. So.
Well, no. I mean, can you please talk about your research and your project and how it is different or compares to existing materiality of timber and stone versus these component parts?
Okay, well, it's a completely different approach, of course, because first of all, I started from like objects which were there. I didn't start from the idea of like, okay, I work with stone, I work with wood, or I work with steel. I just said, okay, let's not start from like creating new objects, but let's use objects which are there. So I started to look like, okay, there is so much waste. What I could reuse. So I looked for like I studied object, and I thought like, okay, maybe this component could create a nice, could be used in a structure. And of course, Sina also at the beginning was like, are you sure? Will it stand? So of course, like already plastic in buildings, it's already a bit weird if you want to use it as an actual structural material. The main idea was like to reuse everything, so to don't use anything like new, or to don't produce anything, but just to reuse stuff. So like the connections are based on this reused plastic object, and also the pipes are reused PVC pipes, also the textile, which also make actually the structure itself quite cheap, because you're like taking waste products and making something out of it. Also, the main idea was that the main idea of using a computational system is that you can use the structure for any kind of shape. Of course, not for housing, because I mean, a housing made of reuse is maybe a bit too forward. But yeah, I mean, you can build every kind of structure. So there is a flexibility in that, like you can design your own shape and then just like build it that way. So yeah, it's I mean, the main difference is a completely different approach from, of course, like what the other guys are doing. Is also, mine is also a graduation project. It's not really.
Well, one thing I thought that was fascinating was that, you know, you're taking the idea of waste and making something productive. And
Yeah.
since we're basically overpopulating the planet, would be one way to think about it. How can architects take responsibility to use maybe the leftover stone or timber, or maybe use machine learning to understand how to use motion paths in the robotics to take that waste and formulate a new other process so that the inputs and outputs can interconnect?
Or even pushing it, my idea was even like pushing it forward, not like not creating more waste, but using the waste which is already there. Because I think that we pushed it so much that we can almost not allow, but that's personal opinion, we can almost not allow ourselves to say like, okay, but I'm not creating waste. Well, whatever you produce is of course new waste, but you're introducing something into the planet, right? So like, what if you can only use what it's already there? Then of course it's more complex. It's for sure introduces a lot of constraints, but that I thought was like the nice challenge in my project. Like, okay, what if you just like, you cannot say, okay, I want to build a cube, but yeah, you cannot do that because then you have to find an object which is already there that allows you to build a cube, you know? So that's, that was the, like the main idea. But
Yeah, thank you. Thank you very much. I think your project, Ginevra, also somehow reminds me of this quote by Adolf Loos. He started his chapter on material, and that what is worth more, a kilo of gold or a kilo of a stone? And probably that's a very silly question, but that's a silly question for a businessman, not for an artist. So, and then these projects sort of show that all materials can be equally important, and it really depends how we rethink a material as a process within a larger, let's say, picture. And this idea of circular, let's say, material that we can use and reuse also is something that we can benefit in other projects we saw today. And I wanted also to ask another question and about the way these emerging fields are somehow redefining or re-questioning the discipline of architecture. And we saw in some of the projects that there's strong will to establish startups, establish firms. And I have this question specifically for Ashish and Tristan. But before going to Ashish and Tristan, I would like to ask Ginevra, because you just started your career as a parametric designer and as an architect. How do you see the role of these, let's say, art and emerging fields in the discipline of architecture? Maybe you can briefly pick on this matter, and then we move to Ashish and Tristan.
yeah, but can you repeat the question because I lost the sound?
My question is, you just started your career as a parametric designer, right? And then you just recently graduated. How do you see the role of these as a fresh, let's say, starter? How do you see the role of these studies in your current and future career?
Yeah, well, of course, what I did for my graduation cannot be directly applied in the practice. I don't see that happening in the near future. But yeah, my idea was to join like not a huge company, but a small company where I could maybe trying to introduce some idea about like robotic fabrication combined with reusing products. Because of course, in a small company, like your voice can be heard louder. So like I really wanted to try to do something. It's not so easy. That's why, I mean, of course, I think robotic fabrication is still not so common in architecture practice. Yeah, I see that it's not so easy for the moment, and but I just wanted to really like but that's my point of view, don't focus only on like, okay, I just like research like robotic fabrication as a researcher, so completely out of the practice, but let's see if we can do even something smaller, but then really in the architecture practice, not like something that then stands in the lab. And but of course that's really difficult, and yeah, that was my approach. I just started, so I'm definitely not there. So, but yeah.
To continue on this topic of let's say emerging fields in architectural design and building industry, I would like to know your opinion, interest, and maybe later, Ashish, how you see your position in a current, let's say, state of the art in building industry and architectural and practices, and how do you sort of foresee the future?
Well, so it was a shift for me since 5 years, as you probably understand, because I started as an architect, and now I'm really, the more I'm listening to you all, I now know that I'm a bit aware of this question of aesthetics, which is not a question that I don't want, because I really enjoy to go into these questions. But I found that to manage to have robotics on site, to manage to, for instance, for the process of Ginevra, where you have to think about how you're recycling the waste. Well, there is a question actually for you. You have to think about how much energy you put in the robots. It's not just about the waste, because if you put more energy in the robots that will operate, well, somehow it's not useful. But I'm not saying that it's not useful, but still it's a question which leads to the problem of global energy consumption, etc., etc. And so it's lead also to recycling, or maybe it's more important to not recycling, etc. But at the moment, I have a huge question in my work, because I really think that we could put robots on site. But the first question you have to ask yourself is it a good idea? Because it will, it's like the debate about the 5G, you know, it's, does it consume a lot of energy? Is it useful? Do we want it, etc.? So for me, the partial answer that I have for the moment is we should develop more link between people that will work with robots. And it's not easy to do that, like to technically answer to that, to have the tool sets to allow people that are not doing robotics, that are not aware of the constraints, to integrate the operation of robots and everything around. So that's the way I think my future and the now, the way I work in the field of architecture is, the question is, how can I put more tools for people that are not aware of the constraints of robotics? But it's not just for architects, because now I feel that architects are more aware of it, but it's more when you ask to craftsmen, they're actually a bit of both, very accurate on how machines works on their topics, but then they still have to evolve on new tools to interact with architects. And we spend too much more time, in my opinion, in the digital worlds without going through to those craftsmen. And especially in France, for instance, where we have, when we have to answer to public, you know, for build a school or this kind of thing, you start with a project but it's really away from the guys that will build it, because it's not, you cannot, for instance, have contact with a specific craftsman, because it's not allowed. And the constitution of the society in France, for instance, don't allow you to interact properly with craftsmen. And for me, the real important thing now is to use the huge amount of knowledge that we are actually now have in the digital world, let's say, and to push it into the craftsman's world, let's say. And I think architects have these roles. I mean, as developers and architects, I really want to do that. Yeah.
Great. This is somehow. Go on, Lee.
Yeah, no, I just had a thought, and it came out of Marina's question. I mean, she mentioned beauty. And since we have the Italian mafia here, I was thinking about Alberti. And it's kind of interesting to think about Alberti's definition of beauty through the lens of additive and subtractive manufacturing. Because this definition of beauty is, and I forget if I get it right now, is that from which nothing can be either added or taken away or altered, but for the worse. Now that's kind of interesting, you know, in terms of additive and subtractive manufacturing. But then it got me to think, actually, I've always thought about that in terms of aesthetics. That's a definition of beauty, is just instead of like, you know, a drawing or something. But actually it also works for structure. It also works for structure. You know, something that's a beautiful structure is something you cannot add or take away for or alter, but for the worse. So I'm not quite sure where I'm going with that, but it kind of got me thinking, as we were talking about how Alberti was not just talking about ornament structure, but thinking about these two together. And it makes me think that his definition of beauty was also, to some extent, a structural definition of beauty. Maybe that's a question for Marina.
Sina, can I answer the question then? Because I will also answer actually Neil's question and Marina's question. So like, well, I was talking about this kind of lack of control that came from the argument of Ruskin, you know. So when he was talking about the stone carving and how like the stone carving was done by hand, and the human hand was creating this kind of imperfection always. And that imperfection, like again, if you see from the David Pye's argument of craftsmanship of certainty and the craftsmanship of risk, this is what comes from, like, you know, human hands and making it by yourself. And this, when you introduce to digital fabrication, the question was how we can create this kind of craftsmanship of uncertainty into the digital fabrication process and use it as a design parameter. And then the second question for Sina, was, well, also like Tristan, I'm not a traditional architect as a sense of architect now for the last 9 years, because I'm doing research in additive manufacturing. But what I feel is that due to digital fabrication, we have a profound chance to change the way we build, because, you know, like we as an architect design things, and then we go to the shop and like buy already ready-made objects. And those objects then define how architecture will actually in the end look. But now with the digital fabrication process, we can actually control what will be that object, you know, what is that object? So we can actually profoundly impact the way we build because of this digital fabrication processes, because we can control this process here. We don't have to rely on a brick manufacturer who will manufacture the brick, which is not the way we had designed it before, you know. So this is what I think that fundamental shift will happen.
And I have a question about something that we are talking about, this idea of object. Even we were talking in some discussion about this kind of idea of field condition of relational thought. But in a way, my question, wanting to look forward, I mean, I want to move forward about how the robotic fabrication can evolve, because we are watching things that we have seen before in a way. So I want to find, maybe in the failures, to find the ways to evolve robotic fabrication to another level. So my question was, that's why my question was in a way delivered to answer, to find or try to build, not now, maybe just let it for the future. How can we plan the future? How not plan, but how can we find the lines to evolve? Because in a way we are a little bit stuck in some things. So and maybe the failures are the answers, because I want to move this idea of the closed object no, the closed object, like this idea that you say, yes, this is here, I can touch it. So I want to move forward for this idea to a more relational thought, to open the design to new ways to think the design, because I don't see this. Okay, just a comment.
Tristan?
Yeah, I want to comment that because for me there is a very particular point that I found interesting. It's how we can also get rid of all the habits that people that work with robots have, actually, because, you know, robots basically are machines to do repetitive tasks and to be efficient. And the problem is, maybe the answer is we shouldn't use robot to be efficient, or in the way that industrial use robots to be efficient, because like cycle time is not something that we care about. And for me, that is one of the answers. The way we need to use design and the way we need to use robots is to say, okay, we need robots to avoid being efficient, but maybe create beauty on this kind of thing. But to do that is to get rid of all the problems of we want to optimize to have a better toolpath and this kind of thing. It's something that come back a lot. And I think in the future, we will have tools to do that efficiently. So the next question is, should we create less objects, but more accurate to a specific context, which lead to, for instance, the 3D printing. You have any kind of form, you can build everything. So that means you can build just one thing. That is accurate, not several.
Great. I think this discussion that Marina and Neil are bringing to the table, this idea of proportion and perfection, and this idea that you mentioned about this additive versus subtractive, a complete thing is something that you can either add or remove something from it. I think that somehow it's a definition. If you put, so obviously back then it was mainly about proportions, but if you put it into today's language of computational design, it might lead to what we know as optimization, right? And in optimization, we have some sort of objectives, and then we optimize our design considering those objectives. So it leads to some sort of perfection, which might not be what we want to get out of architecture in general. So this is something that also, in a way, connects to what Tristan was saying about the fact that within the process or workflow that we consider for these emerging fields, we may also need to consider associations. We may even want to consider the way people would read architecture and perceive architecture. And then this goes beyond this very objective driven or optimization driven design workflows, and somehow also consider other aspects which might be a bit more subjective. So with that, maybe I would also again goes back to what Trin mentioned about the way, for instance, we may want to, or we may need to collaborate with other associations. Maybe this is a kind of a new Freemason kind of movement, which we need to, on one hand, be more in charge of construction, but on the other hand, also be a bit more connected to society. What do you think, Tristan?
Well, I definitely go for the being more connected to society, because I really think that, well, if we can work, I mean, the digital models is one of the answers, because you can send it to people that are actually craftsmen and work with them on the same hierarchy level. And I really, really wish that we can achieve that. As an architect, not in the position of holding everything, but helping others to managing the project with us. And I think this kind of thinking leads to, you know, the comments on this kind of thing. And I really believe that what we are doing in this field leads to this. But, well, It's hard to achieve, I think, but I think this should be the good direction, because at some point we will have to think about energy consumption, these kind of basic things, because, you know, environmental crises lead to these kind of questions. And to answer to these kind of problems, well, we cannot be on our own, because it's so hard to think about everything. If you need to do like life cycle analysis, for instance, it's super hard to do. So you need to make into the project, bring back to the project everybody. And for me, the digital world is a good answer, one of the answers, I would say.
Could I just ask, Sina, I forget who it was from the Bartlett who was talking about the training the robot, robotic arm. I was just intrigued by to what extent AI was involved in that. I mean, obviously it was, but whether there was kind of reinforcement learning that was used to train the robotic arm. I forget who it was from the Bartlett who was presenting.
I think it was me, Julio.
Yeah, yeah. Were you training the robotic arm with reinforcement learning?
No,
okay.
Because there, I can answer So the reason why reinforcement learning was not an option is that actually reinforcement learning works particularly well when you can, is a trial and error routine basically based. It works perfectly well when you have when you can replicate a digital environment, like the simulation actually of the system, and then have like millions of attempts in a digital. But the issue there in my project was actually the simulation of the material and interaction with the tool was not available ahead. So that was the actual final aim of the research. So in that case, using reinforcement learning would have meant to do the trial and error in the physical world. And that would have meant to also use way more time and resources.
Well, except that, I mean, I don't know if you know Mike Haley's work in Autodesk, but they do it in simulation. The point is that you can then really speed things up if you do it in digital simulation, and it's all about training the robotic arm. So I just think that is one area which is actually really challenging right now. How do you use a robot to even pick a brick up and things? And those things are, we take that for granted, but actually it's super difficult in terms of robotic arms and how do you control them? But it's done in simulation as a kind of digital model, as it were.
Yeah.
Yes, I would like to add just a point, very small point. One of the possible answers we should consider in terms of the relation between human and robots, proportions, perfection, art, and so on, is how human controls the robots. From my point of view, what I had seen was Ashish from my previous experience. He is not just taking care of glitching. He is not just eliminating glitch, but also he is controlling the glitch. He is creating the glitch itself to add more possibility to the design and the robot itself. So I think the future is how much you can control the machine, maybe to the level Ashish is doing, or maybe beyond. When we achieve this point of control, we'll be able to do art and perfection and so on.
Ashish, you want to pick up on that maybe?
Well, I agree, and also with Neil's point that this is what I think is the next step, is this kind of machine learning and AI, and like the robot actually learns from the process what is happening, and also this kind of it's very difficult to again teach the robot or the machine learning the tacit knowledge, which also Julia was talking about, and the material knowledge. So this might take some time, because this comes from experience. Changes in the environment also affects the material, the way it behaves. So, but the next step is again to teach the robot the way we do things, and then to make them actually to then repeat those tasks.
And if I may add a really small comment, yeah, sure. In everything that's been said, I think Sina asked how it's going to change, the process, or even just, the way we think about architecture. And I think, in that sense, everyone is setting up, you all are designing processes, right? And I think that's why it's so interesting, because in that sense, change begets change, because the process that you're showing, other people will pick up and actually alter it. So in that way, you already create an open-ended reference, because you're not only designing an object that we can observe, but you actually introduce us to a way of thinking. And I think that is really powerful, because then, you know, the process is actually something that challenges people to think differently. And I think that's really beautiful. I mean, with Tristan, I think what's super interesting is that, you know, we know more and more that when people grasp an object, it's actually a control movement that is kind of not adjusted to a certain point. And then we get to a point where there's like super, you know, feedback loops going on, because your brain needs to actually like adjust to the environment that it's grasping towards. And I think the robot operates differently, but I think you have both ways learning from each other, because one is mapping very specifically, the other one is more open-ended, the brain. So I think that way of thinking already is a huge revolution. So I think it's really interesting. Sorry, just a comment. But
I just wanted to build off of Victoria's comment. Sorry about that, Sina. I just wanted to say that I'm very excited to see the research today, and to individually be messaging you behind the scenes, because I'm so curious of where this is going to lead in the future. And Sina, I think, brought an interesting question, like how do we imagine this process, and then how do we I guess forward along the culture of architecture, the client, the professional pipeline, and academia to be comfortable with this language, because we're still, I think we're in between this generational power transition. And I think there's a lot of, Neil brought it up, why aren't we using these methods already, machine learning, reinforcement? Maybe that should be the baseline of a lot of academic, I would say, curriculum. Like, who knows what the baseline is? But I know in the sciences, what they do is they go for the standards, they build on the high standards, and then they keep incrementally moving forward. So anyway, maybe Neil knows more about that.
I would just say that I think that AI is absolutely, for sure, going to be taught in every single discipline in the academic curriculum. I mean, it's my own university is planning that, and I'm sure by the end of the decade, we will find AI being used everywhere. I just wanted to add as a sort of point, because I was really blown away by these presentations today. So thank you very much. But the term pipeline, I was thinking about the term pipeline in a different sort of way. I was thinking, well, it's really amazing to see these young researchers, and I'm sure they're going to become amazing professors in the future. And just going back, I was just saying to one in the side chat, I was teaching at the AA when Akim Menges and Neri Oxman were both students. It was an incredible moment, actually Andrew Cutlass too. And you could see the future there moving through. And I think today I got a glimpse of the future today as well. I think this is really encouraging to see this work. It was a fabulous display. So I just wanted to thank you. I think I was blown away by it.
Yeah. Thank you, Neil. Interesting session, and I think we can move to the last comment or questions, and we can close this session. I'm sure there are a lot of other points and interesting questions to address, but I would like to ask the committee or the speakers to bring the last comment or questions, if there is any.
Yeah, I have one final comment. It's a little bit specific in a way, but I would like to say that maybe this idea of how are we planning the future, how we see the future. I think that we need to consider the future far from certain categories that we still repeating. I think that the idea of categorization, I hear different categories today, that I think that we need to move on from certain like modern or postmodernism or these kind of categories of like deconstructivism or that we spoke already in other sessions, or about the concrete, discrete, and I don't know, these kind of categories. I think that really we need to move on from this. And I think that one way to do it is to move on from certain readings that we are consuming today, and we need to criticize them, and we need to move on, and we need to write our own things. And even if we construct a new category, I think that the next step is automatically criticize it again and move on, because now we're talking about robotic fabrication. In a way, it's not a category, because we are talking about made of makings, which is, I think, is what it plans, like a more open, this idea of more open process that can involve all this difference that we saw today, because we are not all the same. So just this final comment about the categories that I hear today, just to get my point about this.
I wanted to reinforce what Marina was saying. I think that I'm coming at this from UCLA West Coast science and military perspective. And I've left the last decade of material science and engineering and physics to look at architecture. And there's a whole new territory that I know we can explore, but I think Neil can speak more about the decades of how the profession has evolved. How are we as new leaders of the field going to push the powers that contain our creativity forward? I mean, I'm still pondering that question after a few decades, and my professors have suffered from it a lot. And I know Neil probably has more ideas, and that's why I'm here. I'm very hopeful.
Do you want me to answer that? But I don't know. I mean, all I would say is that I could see the future here now. My problem with some professors, they're stuck in the past, but here I can see that there's actually going to be a rejuvenation of the academic community through, I think, some really, really, really smart individuals. I'm quite optimistic. I mean, I think that things are going to be changing in the future, and we have to be alert to that, of course. We won't be in the same world in 20 or 30 years' time with the singularity happening when automation and AI is really kicking in. And I think it's therefore absolutely important that, that we have professors who are looking forward to that kind of world and not looking backwards. I think that I'm left full of confidence that there's a pipeline of new professors appearing who are really super smart. I'm not sure what else to say, but the future is emerging as we talk. I mean, particularly this year, I think we've seen that we've seen history in the making in a kind of strange, interesting kind of new way. And I think we have to be alert to that. I think we have to be alert, as we have in our discussions about education, to think about how education is changing. And it's been, I think all I would say is it's a radical moment of shift and change that we're going through, that I think in the future we'll look back on as one of the kind of astonishing kind of events like May 68 or something that's really going to change the way we look at things. But I think we're okay. If we're in the hands, if our education of the future is in the hands of these guys today, I'm confident.
Thank you very much, Neil. I think
yes, I'll do my best until I had a conscious robotic chef in my kitchen to understand well how they think, and then we can think of how we can implement in architecture. in Australia, I can see a lot of videos in Australia, there is robotic arms. You can buy a scrambled egg that is made by robot. So the future is when they are used in our daily life routine, and then we can implement more specific in our field. But the last thing I had to mention, there is a TV series on Netflix called Altered Carbon, and how people can move their consciousness into robots and into other slaves. I think this is how future can be.
Interesting.
I mean, just to say, Digital Futures about 4 years ago, I think it was, maybe 5 years ago, we had a robotic arm making a cocktail, a kind of shaking it. So that's, I'm sure, the future too.
Great. I think that's a very interesting topic too, like how automation can give us more space to be more efficient and to be more human. That's interesting topic.
Everybody can make scrambled eggs still I hope that everybody can make their scrambled eggs, because I mean, do you really should use the robot for that? I mean, also in terms of energy, like you can make your scrambled eggs probably on your own, and that's more effective. But yeah.
Exactly. Okay. Obviously, there are some different points of view whether we should do our own things or automate everything, which is great. Probably this will be addressed in the future session. With this, I would like to maybe close these sessions if there is anything else. We can probably pick up in the future sessions. We would have 2 more sessions on robotic fabrication next week, so on the 17th of October. And with this, I would also like to thank everyone who joined today, and also our audience who were with us until now. So thank you, and hope to see you later, and we keep in touch.
Thank you, everyone.
Thank you, everyone.
Bye.
Bye-bye.
Thank you.
Bye. Thank you.
Bye-bye.
Bye.